Hi there. Now we're going to talk about maxima and minima problems. Well, we're going to start talking about it. This is going to cover several lectures for us. So let's define a critical point first of all. Let's suppose z equals f of xy is a function defined on an open set containing the point x sub 0, y sub 0. Then x sub 0, y sub 0 is a critical point of f if one of the following two conditions holds. All right, so either the first partial of f at that point are both 0, or one of those first partials does not exist. So this is somewhat similar to the definition from Calc 1. So let's do an example. Let's find the critical points of this function here. So step 1 is to find the first partial. So we see that the first partial with respect to x is going to be 3 times x squared minus 3 times y. And the first partial with respect to y is going to be 3 times y squared minus 3 times x. Both are defined for all x and y, so we only need to look and see where they are both simultaneously 0. Okay, so let's just set them equal to 0. So 0 is going to be df dx, which is 3x squared minus 3y. Let me just write that as that is equal to 0. And df dy, which is 3y squared minus 3x equals 0. So there are a couple ways we can go about this. Let's just look at the first equation. So the first equation gives us that y is equal to x squared. And then what we're going to do is we're going to take y equals x squared and plug that in for y in the second equation and then solve. Since this is a system of nonlinear equations, we have to be a little careful. All right, so I'm going to get 3 times x squared, quantity squared, minus 3 times x is equal to 0. Let's see, that's 3 times x to the fourth minus 3x equals 0. Let's just divide through by 3 because we can. We do not want to divide through by x, right? Because, well, x could be 0 and that would be bad. Okay, so that gives me x to the fourth minus x is 0. Factor out an x. X times x cubed minus 1 is equal to 0. So I get x equals 0, or x cubed minus 1 is equal to 0. And that, of course, if x cubed minus 1 is 0, x has to equal 1. And so if x is equal to 0, then y is equal to 0 squared, which is 0. And if x is equal to 1, then y is equal to 1 squared, which is 1. And so the critical points are therefore going to be 0, 0, and 1, 1. And that's the idea. Okay, so now let's move on to local maxima or minima. So the definitions are basically, I would hope, what you would expect. Right, we have a function z equals f of x, y. It's defined and continuous on an open set containing the point x sub 0, y sub 0. F has a local maximum at x sub 0, y sub 0 if f evaluated at that point is greater than or equal to f at any other point in an open disk centered at x sub 0, y sub 0. That gives us then the local maximum value is the function evaluation at that point. And similarly for the minimum, right, f at that point is less than or equal to any other function value in an open disk centered at that point. And the function evaluation at that point gives us the local minimum and the global maximum and global minimum, right? If f at that point is greater than or equal to f at any other point in the domain, we have a global or absolute maximum. And if f is less than or equal to f at that point is less than or equal to f at any other point in the domain, of f, then we have a global minimum or absolute minimum. So if f is either a local, let me try that one more time. If f of x naught y naught is either a local maximum or a local minimum, then it is called a local extremum. Now we know from Calc 1 that extrema are functions of one variable occur at critical points, and the same is true for functions of more than one variable. In fact, we have Fermat's theorem for functions of two variables. And it says, let z equals f of x, y be a function defined and continuous on an open set containing the point x sub 0, y sub 0. Let's suppose that the first partials of f exist at that point. If f has a local extremum at x sub 0, y sub 0, then x sub 0, y sub 0 is a critical point. Okay, so let's actually prove this. And how we're going to prove this is, well, we're going to be a little sneaky. Let's suppose that g of x is equal to f of x comma y sub 0. And let's suppose that f of x, y has a local extremum, a max, min, it doesn't really matter for our purposes, at x sub 0, y sub 0. Well, then that tells us that g has a relative extremum of exactly the same type. Right, so it's the exact same kind of local extremum of f at x equals x naught, because g is just a function of x. Okay, but then that tells me that g prime of x sub 0 is going to be equal to 0. But what do we know? G prime of x0 is the same as the partial with respect to x at x sub 0, y sub 0. And so that tells us that the partial of f with respect to x at x sub 0, y sub 0 is 0. Similarly, let's define h of y to be f of x sub 0, y. And again, assume that f has a local extremum at that point x sub 0, y sub 0. Then, as before, h has a relative extremum of exactly the same type, right, of the same kind as f at y equals y sub 0. And if we repeat a similar argument, right, so we would know then that h prime of y sub 0 is 0. And since h prime of y0 is equal to the partial with respect to y of f, then we know that the partial with respect to y of x naught y naught equals 0. And so therefore, since the first partials are equal to 0, x naught y naught is a critical point. Awesome. Now, I'll bet you'll be really excited at what we're going to do next. We're going to use the second derivative test. Well, the second derivative test is a little bit different here. Okay, a lot different. Okay, so there's one more type of critical point besides the extremum, besides the local max min, and that's called a saddle point. So if we have a function z equals f of x, y, the point x naught, y naught is going to be a saddle point if the first partials are equal to 0, but there's not a local extremum. What? Pretty cool, huh? All right, second derivative test. Suppose z equals f of x, y is a function, and the first and second order partial derivatives are continuous on some open disk containing the point x sub 0, y sub 0. Let's suppose that the first partials are equal to 0 at that point. We're going to define a quantity, and that quantity we'll call it capital D. It's going to be the The product of the second partial with respect to x and the second partial with respect to y minus the mixed partial evaluated at the point squared. And so here's how it goes. If that quantity D is positive and the second partial with respect to x at that point is positive, then F has a local minimum at x sub 0, y sub 0. If D is positive and that second partial with respect to x is negative, then F has a local maximum at the point x sub 0, y sub 0. Okay, fine, not finally. If D is less than 0, then we don't have to do anything else. We know that F has a saddle point at x sub 0, y sub 0. And finally, if that quantity is equal to 0, then no conclusion can be drawn, and we need to use other techniques, i.e. graphical or something like that. I should say e.g. other techniques are needed to classify the critical point. So the textbook, figure 4.49, gives some examples of local extrema and a saddle point, so you can get a visual as to what these guys look like. So we have local minima, local maxima, saddle point. Okay, let's do an example. Let's find and classify all the critical points of this function, and then that's going to actually conclude today's or this particular recording. And then next time we're going to talk about absolute maxima and minima, which is going to be much more fun. Red work. Okay, so here we go. Let's do the first partials. So the partial with respect to x is going to give me 6 times x times y minus 6 times x. And the partial with respect to y is going to give me 3 times x squared plus 3 times y squared minus 6 times y. Okay, so to be a critical point, since those partials exist everywhere, they have to be equal to 0. So we have the system of equations. Partial with respect to x is equal to 0. Partial with respect to y is equal to 0. Okay, so let's look at the first equation. The first equation, we can factor out a 6x. And so this one's going to give me 6x equals 0, or x equals 0, or y minus 1 equals 0, so y is equal to 1. And so we just plug those into the second equation. All right. So if we let x equal 0 in the second equation, I get 3 times 0 squared plus 3y squared minus 6y is equal to 0. I can factor out a 3y, so I get 3y times y minus 2 is 0. So that's going to give me y is equal to 0 or y is equal to 2. And if y is equal to 1, I get 3 times x squared plus 3 times 1 squared minus 6 times 1 equals 0. That gives me 3x squared minus 3 is equal to 0. So I assume everyone can get this, that x is going to be plus or minus 1. So what are our critical points? We have 0, 0. 0, 2, 1, 1, and 1, negative 1. Oops, sorry, got that backwards. It was x that was plus or minus 1. Okay, let's try that again. Critical points are 0, 0, 0, 2, negative 1, 1, and 1, 1. All right, now let's compute the second derivatives. Okay, so the second partial with respect to x gives me 6y minus 6. Second partial with respect to y gives me 6y minus 6. I feel a pattern here. And the mixed partials, both are equal to, let us see, I'm going to get 6x. Awesome. So D is going to be equal to 6y minus 6, that quantity times itself, 6y minus 6, minus the quantity 6x squared. Okay, so that's just 6y minus 6 quantity squared minus 6 times x squared. All right, let's take the points. So negative 1, 1. D is going to be equal to 0 squared minus negative 6 squared, which is 36, which is positive. And the second partial with respect to x is 6 times 1 minus 6, which is 0, which means, oh, what am I, oh, that's a negative 36, which is negative. So I'm just doing silly things here. So second part, so D is negative, so saddle point here. For 1, 1, we get the exact same thing, right? We get minus a positive 6 squared, which is negative 36, which is less than 0, so saddle point. All right, what about 0, 0? At the point 0, 0, D is going to be negative 6 quantity squared minus 0 squared, which is 36, which is positive. And now we need the second partial with respect to x. At that point is going to give me negative 6, which is less than 0. So we have a local maximum. Finally, 0, 2. So for 0, 2, D is going to give me negative 6 squared minus 6, well, minus 0 squared, which is 36, which is positive. And my second partial with respect to x is going to give me a positive 6, which is greater than 0. So we have a local minimum. So to summarize, negative 1, 1 and 1, 1 are where we have a saddle point. I can identify it, I just can't write it. So we have saddle point, and 0, 0 is a local maximum, and 0, 2 is a local minimum. And that concludes the example. So as I said, next time we're going to talk about absolute maxima and minima. So have a great day until then.